Alrighty, welcome to our video here on graphing exponential functions. We are going to be graphing these, and we're going to be looking at some real-life situations in which math, and in particular exponential functions, are used to figure some things out. I believe this is probably an example that we should be worried about. In July 2002, National Geographic ran the article that said that they talked about nuclear waste, and they said that we have 77,000 tons of waste, and it's radioactive material that's going to be dangerous because it will take 240,000 years for plutonium-239 to become safe. And plutonium-239 is what's used in nuclear missiles, along with uranium. And then I also believe that plutonium-239 is also used in nuclear power plants, or it's a byproduct, one of the two. I'm no chemist or a science teacher. I'm just going to share with you the math behind the science. So scientists, when they talk about a half-life, they're referring to how long it'll take for half of the sample to decay. So I believe plutonium-239 has a half-life of 24,100 years. Whoa, that's a lot. Let's just use a easy example here. If there's 100 gallons of plutonium-239, when will it not ever be around? And it looks like it turns into lead when it becomes not usable. So 100 gallons is 100 gallons. This is going to be year. Let me make my table a little differently. You guys pay attention to this. You can just watch this part. So years, and then this is gallons. So we have 100 gallons. What year is this going to be? This is going to be year 0. How many years until it becomes 50 gallons? Well, that's going to be 24,100. And then what about 50 gallons? How many more years until it becomes 25 gallons? Well, that would be year 48,200. And when I say year 48,000, that's 48,000 years from this year. You know, if we had 100 gallons today, that would be 48,000 years from this year. All right. And so how about when it becomes 12.5 gallons? And so we notice that each half-life, it just becomes half. And then we also add 24,100 to the previous one. That would be what? 72,300. And so if we notice that what's half of 12.5, that would be 6.25. It's half of that. That's going to be 3.125. And it just keeps becoming half and half and half. So if we keep taking half of the half from the previous half-life, will it ever completely go away? If you understand your math, you'll realize that it never completely goes away. Because once we get this down to something super small, for example, like say if we had half of a gallon left, well, half of a half is a fourth, and then half of a fourth is an eighth, and then half of an eighth is a 16th. And we notice that these numbers keep getting super, super small, but there's always just a little bit left there. So in understanding the math behind this, it kind of helps you understand the science behind this and why this is such a big deal for not just our country, but possibly our world. Because if the United States has 77,000 tons of waste, what about some of these other countries that are out there that are also producing nuclear waste? So, this is a short example here for you. I'll let you know what we're getting into and why exponential functions are useful. Exponential functions, if you want to write down some of these, you can, or you can just pay attention. Basically, exponential functions have the variable as an exponent, and you can have it as x plus 1, or you can have negative. And this is just general exponential functions. You've worked with linear functions, and linear functions have always had, let's see, here's an example of a linear function. Linear functions have always had the x to the first power. You've also worked with quadratics, where quadratics would have, what do we have? The exponent, well, x has an exponent of 2. It's a quadratic function. Linear has the x has an exponent of 1, but if you notice, an exponential function has an exponent of x. And I say functions, here's the function, and then this one is just, remember, f of x and y mean the same thing. So, okie dokie. Those are some examples of what exponential functions look like. And here's a specific situation in which we use exponential functions. Just pay attention to this part. I will come to some problems where you can write some stuff down. If you feel like you need this, you can actually write it down. There's another equation in a few slides which I will have you write down for exponential growth. This is exponential growth. And let me move to the next slide, and I'm coming back quickly, but I'm moving to the next slide. You see y equals a times b to the x power? Look at exponential decay here. This is exponential decay, and it has the same, equation. Now I'm back on exponential growth. The difference between them is this situation here. Okay, is this situation here. So, here's the equation, here's the function. Both of them represent exponential growth. And exponential growth, a is greater than 0. So this number out front is greater than 0. And we notice in our example we have 1. That would be greater than 0. And b is greater than 1. This is the reason why it is exponential growth, is because b is greater than 1, which means what we know about exponents is that if this number here is greater than 1, when we raise it to the exponent, it should get larger. So here's our example. For this example, each time x is increased by 1, y increases by a factor of 2. So let's make our table here. You know what? I started at 0. Let's start at some negative numbers. And this is how you can graph exponential functions without technology, without a calculator. You just basically make a table and see what it does. So follow me here. First one, x equals negative 2. So let's plug it in here. Y is equal to 1 times 2 to the negative 2 power. What does it mean to have an exponent to the negative power? Well, it means you have to move it to the other side of the fraction bar. And I'm sure there's an explanation out there that says something about it being the inverse. I always like thinking that you move the number to the other side of the fraction bar. In this situation, we have 2 over 1, And 2 is being raised to the negative exponent. So 2 goes down to the bottom of the fraction bar, and it gets a positive exponent. We know that 2 to the second power is 4. And so what's 1 times 1/4? 1/4. So now in the next situation, let's let x equal 1. I'm sorry, -1. So that would be 2 to the negative first power, which means you send 2 to the first power to the bottom of the fraction bar. And what is 1 times 1/2? 1/2. For the third situation, let's let x be 0. And so basically, this is all we're doing. We're plugging these values in. 2 to the 0 power is 1, and 1 times 1 is 1. Now x is going to be equal to 1. And since x is equal to 1, I do not need to put it up there for the exponent. We know the invisible exponent is 1. So 1 times 2 is 2. Let's let x equal 2. So that's going to be 1 times 2 squared, which is 4. And for the third situation, let's let x equal 3. 2 cubed is 8. And 1 times 8 is 8. And you notice how this is growing as the values of x get larger, the function then grows. And in this situation, it's going to be doubling because it increases by a factor of 2. And so here at this year on the graph, that would be 5. No, that's 1,000. At 10 years, that's 1,000. At 11 years, that would be 2,000. At 12 years, that's 4,000. At 13 years, 8,000. And at 14 years, 16,000. I bet you 15 years is going to be 32,000, and 16 years will be 64,000. Obviously not going to fit on the graph. This is an exponential growth. And you notice how it starts out fairly slow, starting out, and then it starts getting large real fast. So keep that in mind, exponential growth. Exponential decay, same type of situation. Same type of situation. We're going to come up with a different example here because we're going to talk about right here. B is between 0 and 1. And so this means that this value is between 0 and 1. And 0.5 is between 0 and 1. And that means that it will be decaying. It will be going away, getting smaller. So our situation, let's go ahead and make a table of values here. Let's go ahead and start with some negative numbers. Alrighty then. I hope you don't mind if I change this 0.5 to a fraction. You could see probably at the beginning, the first example of plutonium, I had to stop and think a little bit with the decimals, make sure I was getting those right. And with fractions, usually we don't have to stop and think as much because I tend to think those are easier to work with. So let's look here. Let's go with -2. So -2 is right here on the graph. We notice that the graph doesn't have a -2 value. Will it have a -2 value? Let's plug it in and see. Y is equal to, maybe it's just off of the graph. Maybe the graph just keeps going. 1/2 to the -2nd power. All right, just let me kind of go through a real quick refresher if you guys don't remember this from algebra. So when you have a negative, well, when you have an exponent outside of parentheses, everything inside gets the exponent. And then because those have negative exponents, they get moved to the other side of the fraction bar, which means the 1 to the negative second power gets moved down to the bottom with a positive second power, and the 2 to the negative second power gets moved to the top with a positive. Okay, so we're looking there. So we have 2 squared, which is 4, and we have 1 squared, which is 1, so 4 over 1. So 1/2 to the negative second power should be 4. And 100 times 4 is 400. Alrighty. And what about if we change this to a negative 1? You should know that anytime you have a negative exponent, it means that you have the inverse. So you can do it the way I previously showed you, or you can do it this way. Negative exponent means it's an inverse. So what's the inverse of 1 over 2? One over 2 becomes 2 over 1, and then exponent becomes positive. And so 2 over 1 is just 2 squared, which is 4. And that's the same thing we got in the previous example, except this one here, we didn't have to deal with the fraction as long. So that doesn't really change if it's a negative 1. You can still think about it as 1 to the negative 1, 2 to the negative 1, and then they go to the other side of the fraction bar with positive exponents, which then leaves us with 2. You could think of it like that. Ideally, I'm hoping you learn some of these basics and you realize this stuff, that if we have 1 over 2 to the negative 1 power, it's just 2 over 1 to the positive 1 power, which is just 2. So hopefully you get to see some of this stuff inside your head without actually doing all of this that I'm doing up here. Hopefully all that is happening in your head. So back to our situation, if we have 1/2 to the negative first power, we're trying to fill in this part of the table. 1/2 to the negative first power, remember it's the reciprocal, and 200. And I think I just said the reciprocal there. And 1 over 2, the reciprocal of that becomes 2 over 1. And you'll notice the I said reciprocal here. I just wanted to let you know that earlier I said inverse, and now I use the word reciprocal. I'll probably be using reciprocal from now on, but you may hear that word inverse used for this situation with negative exponents at some points. So, can we move on? Let's move on. Now, what about if we have it as 0? 1/2 to the 0 power is 1, and so 100 times 1 is going to be 100. And what about if we plug a 1 in there? What's 100 times 1/2? It's 50. Now, I'm sure you can see the pattern in the table, but the whole point is me showing you a simple example, so that way you can do this when it's not so simple. What is 1/2 squared? Well, that's 1/2 times 1/2, which is 1/4. And 1/4 of 100, if you're breaking that up into fourths, you get 25s. And what about 1/3 or 1/2 to the third power? Well, that means we have 1/2 being multiplied by itself 3 times. So you want to get 1 times 1 times 1, which is 1, and 2 times 2 times 2, which is 8. And 100 times 8 is going to be, I'm sorry, 100 times 1/8. That's going to be 100 over 8. And you can reduce the fraction, divide by 4, and you get 25 over 2. You can put 25 over 2 or you can put 12.5, whichever helps you graph. And so you keep going along this path, and so let's say we have 2, 25, we have 3, 12.5, you're going to have 4 and 6.25, you're going to have 5 and 3.125, and you keep going along the list here. Keep going along the list, and you notice how it gets close and close and close. Well, when it keeps getting closer to that 0 for this, that's going to be y equals 0. That's the equation for that red line that I just drew on there. I know it's the x-axis, but that's the equation, y equals 0. When that function keeps getting closer and closer to y equals 0, we call that an asymptote. And we know that it's not ever going to touch. Not ever going to touch. Let's look at this in a graphing calculator. So let's type in 100 times 1/2 raised to the x power. And we could graph it, but we don't really need to graph it because the graph's right here. What I'd like to do is I'd like to look at the table. Table is right up above graph in blue, so let's press second and then table. And so this is a table that we just created, 150, 25, 12.5, so forth. And you notice, look at the numbers here. 1.5, 625.78125, 0.39063, 0.19531, and you notice what's happening? It's half, and it's half. And it keeps getting smaller, but is it ever going to touch 0? Right here, it got so small that they put it in scientific notation. And we keep scrolling through there, and the scientific notation just keeps getting larger. I just keep clicking the button, and it's not changing at the moment. So, looking there, keeps getting smaller. Not ever going to touch 0. And I know that it looks like it's going to touch 0, but this is why you have to use your intelligence and realize that it's not ever going to. Exponential decay. Okay, this is how you graph without a graphing calculator. I quickly showed you there in another example. All we had to do with a graphing calculator, we typed it in and pushed graph, and that's how you graph with a graphing calculator. Typically, you remember back when we were talking about this right here? -2, and I said, well, can you have -2? Ideally, this is year 0 on some real-life situations, and you don't typically go back to the negative numbers when you're talking about real-life situations. But in some contexts, you may, or if it's just this right here, and it says, hey, here's your equation, I'd like you to graph it. And if it's just a math situation, there's no real life situation involved, it could go back into the negatives. Now, it will never go below there in the example that we have. There are some exponential functions that will go down into that quadrant there, quadrant 4, and they flip around. They do all kinds of things. So I'm not going to say they never do that, but the one situation that we're talking about won't do that. So you have to take into context whether you're talking about a real-life situation and determine what the domain and range will be. And there's some vocabulary terms we have to understand. Domain and range. So let's quickly discuss that. Domain and range. Domain is all the x values. So we know that this graph is going to keep going forever in that direction. And x talks about left and right. And if we keep talking about this situation, if it's just a mathematical equation, the domain is going to be all real numbers, all real solutions, something like that. The range talks about the y values. Well, what values for y can we have? Well, we notice it will not go below 0, but it's every number above 0. We notice how this gets really, really close to 0. So how do we show that it's going to be all values? The range will be all numbers greater than 0. And we notice we didn't put greater than or equal to because 0, it'll never touch 0, so it's not. 0 is not part of that. All numbers greater than 0. Now, if it's a real-life situation, this domain might change. If it's a real-life situation, that might eliminate those negative values and say that it's going to be all real numbers greater than 0 if it's a real-life situation. So you have to keep remembering domain and range and understanding what it's asking of you. Okie dokie, that's the introduction. I'm going to have one more video which we take real-life situations, plug them into some formulas, and work them out. I told you there's going to be some exponential growth and decay formulas. Those are coming in the next video. And then we're also going to do some graphing with technology, graphing calculators in that video also. So keep an eye out. That'll be posted here shortly, and you can get both of them done. And then you'll know how to graph exponential functions with and without technology.